Okay.
Can you see the screen?
Yes, we can see and we can hear you. The floor is yours.
Okay. Hello, everybody. My name is Cheslin, and I am a PhD student at Luleå University of Technology. And today I will be presenting my work on adjustable guidewing system in hydraulic turbine draft tube, a concept to control rotating vortex rope or pressure pulsations. Okay, the agenda, I will present briefly some background and then objective of my presentation and rotating vortex rope study, mitigation study we have done so far, and some conclusion and current and future work. So as we know, hydro turbines today can operate with very high efficiency, almost up to 96% at the single operating condition called best efficiency point. But usually when we move away from this operating condition, the performance of the turbine is affected. This performance of the turbine is affected significantly at lower operating conditions, where formation of rotating vortex rope, a vortex breakdown phenomena, is prominent. So what is, okay, yes. So what exactly is rotating vortex rope? It is a progressive type of helical vortex, which is caused by high swirling flows in the draft tube at lower operating conditions, as you can see in the video. And this phenomena affects the efficiency of the turbine significantly. Some of the main causes of the formation of RVR is a lower flow rate in the draft tube and higher flow rotation or higher flow swirl in the draft tube. So how do we control it? What we intend is to introduce a set of guidewing system in the draft tube. And to do so, I have divided my work into 4 stages. First one is stage 1, where I study the flow behavior within Francis 99 turbine draft tube, which is available to everyone. And from there, I will, in stage 1, also we have to bring out a way to perform the simulation faster. So we develop a reduced domain modeling by just considering the draft tube, which leads to stage 2, where we design the ideal guidewing design in this reduced model. It is strictly to understand the dimensions of the guidewings with respect to the positions, cord length, span, number of guidewings needed in the draft tube, etc. And stage 3 is development of more realistic design, which has a CFT as well as FSI analysis with 2 materials. And the final stage, which we will be focusing on from here onwards, is the experiments and the guidewing system manufacturing, which is ongoing. So the turbine specification, we are using Francis 99 turbine from NTNU, which is available on the website for research. The turbine has a spiral casing, distributed domain with 14 stay wings and 28 guide wings, a runner domain of diameter approximately 350 mm. With 15 main blades and 15 splitter blades and a elbow draft tube. Okay, in stage 1, to analyze the flow within the draft tube, we consider just the draft tube domain, and we try to do the analysis by just mapping the flow the velocity profile at the inlet of the draft tube from the runner draft tube interface, and and try to imitate the flow phenomena with the complete model. Why do we intend to do this? Because we wanted to produce something that is feasible to analyze a variety of Guidewing system designs in a shorter span. Otherwise, if you consider the full domain, you know, the mesh is a problem because it has a huge amount of mesh, and considering the time constraints, a reduced model is a better idea. So we use the source code ANSYS CFX and turbulence model as K epsilon. With the reduced modeling, we were able to imitate the flow behavior, flow characteristics in the draft tube of the Francis 99 turbine at part load operating conditions. Simulations were performed significantly faster, and the reduced model was considered quite useful for Guidewing system design process, where multiple simulations were performed at a time. Stage 2, we wanted to, for the ideal Guidewing blade design, there were certain factors that was considered for the design process. There were 5 factors, out of which 3 are extremely important. The first is position. It is, we don't know where to, at the beginning, we didn't know where to position the Guidewing. Plus, the inlet and the outlet angle of the Guidewing system is a subject of position. So it depends where you position the Guidewing, the inlet of the Guidewing system and the outlet of the Guidewing system changes accordingly. The number of Guidewings, 14, 7, 3, and 2. We choose these numbers in accordance with the Francis 99 turbine. As I mentioned here, the turbine distributor had 14 stay wings. So we started with 14, and then we reduced it by 50% and then lessened it further. Chord length, it was in percentage of runner radius. So we had 3 cases, 21.5%, 43, and 86% of runner radius. The span of the Guidewing is 15 and 30, and the inlet and the outlet angle of the Guidewing system, as I mentioned, is subject to the position. So there were some arbitrary assumptions to be made. For initial analysis, we just put the Guidewings right under the runner exit or very close to the inlet of the draft tube. And this was not a proper design. It was just to see if the concept is working or not. So we just designed as a single blade model and performed the several analyses. So just to brief out the result, we figured out that only 3 or 2 set of Guidewing system is enough to control the rotating vortex rope within the draft tube. And the chord length is needed was approximately 86% of runner radius, and the span would be 30% of runner radius. With this, we were able to suppress the RVR approximately up to 98% for both cases. However, this method has a drawback because it only considers the draft tube. It is far from the realistic condition. So it is very important to include the upstream conditions. So we had the initial dimensions. We further optimized the Guidewing design according to the realistic conditions, and we splitted the chord length into two equal halves. So the intention here is the lower one will remain stationary and the upper one will be moving according to the operating conditions. So at part load, it will be part load. At BP, the angle will change, and so in high load operating condition. Interestingly, we found that placing the guide wings right under the runner exit is not a good design at position 1. So we had to investigate further by moving the guide wing a little lower at position 2 and further lower closer to the draft tube elbow, position 3. And what we found was position 2 gave the best result, almost 97.4% of reduction in rotating component of the RVR, plus some increment in the value of CP within the draft tube was achieved at position 2. However, for 2 guide wing system, this the results were not that great. It could only suppress the RVR up to 63%. So overall, 3 guide wing system is the best result as far as the numerical analysis was concerned. Some flow, the circumferential velocity at different positions within the draft tube. We understand that if we compare plane 1 and plane 2, there was not much happening in the draft tube. Only the significant changes in the flow was seen at plane 3 and plane 4. So the flow is changing midway the Guidewing system. To be brief out about the upstream conditions, I had a look on briefly how the flow changes upstream. There is flow change in the upstream, but when you look at the efficiency of the runner turbine head torque, there is an improvement in that. Looking onto the circumferential velocity, if you see in the reference case, there is a zigzag or movement of the RVR. But when you put the Guidewing system, this is more aligned straightly. So the rotating component is reduced, and the vortex becomes, the rotating vortex rope becomes a vortex core region within the draft tube. And speaking about the axial velocity, again, in plane 1 and plane 2, there is not a significant change, but plane 3 and plane 4, in both cases show that there is axial velocity increment, especially at the draft tube wall region. So this study until here was done at part load operating condition. However, we want some design that could work for other operating conditions as well. So to do so, we need some clearance near the draft tube wall so that the upper Guidewing can move according to the flow operating conditions. Like at BP, the angle will change, which I will explain in the next slides. However, and the lower Guidewing is stationary, so there is no change to be made. And the thickness of the Guidewing will be varying thickness from 2 millimeter to 4 millimeter. To do this, how we reach to these numbers, there is a quite detailed report that we have submitted in one of our deliverables. I think it should be available online for everyone to read. To perform FSI for the design, we considered the worst case scenario. And to consider the worst case scenario, we need the Guidewings closed up to certain angle and in the highest operating conditions. So at present, the Guidewing can be moved for plus and minus 45 degrees, and the highest load is at high load operating condition. So we found two materials, aluminum alloy and structural steel, and they both give fairly good result in terms of structural stability. However, in terms of deformation or deflection, we think that structural steel is a better choice than aluminum. So when we are building the Guidewing system and the draft tube cone for the experiments, we will go with the structural steel. So I wanted to present different angles. So this is at part load. The angle would be approximately somewhere 32 degrees, and the lower blade angle is 10 degrees. As I said, the upper blade angle, upper blade angle is adjustable according to the flow conditions, and the lower blade is at BEP. So the lower blade angle is 10 degrees. And for BEP, both will be 10. We analyzed 4 cases here by putting it at 0 and 0, and then 10 and 0, 0 and 10, and then 10 and 10. In terms of flow separation and turbine properties like efficiency, the best is to keep 10 and 10 because we don't get any flow separation. And in the high load, we have 35 and 10. So here you can see there is, of course, some flow separation. As I said, the flow is affected midway the Guidewing system. So there is flow separation here. However, if you see BEP and high load, there is no flow separation happening. And we want to make a design which will not affect BEP and high load significantly, but part load, the RBR can be controlled. So conclusion on the current and future works. RBR can be mitigated by a set of thin Guidewing system in the draft tube of the Francis 99 model turbine. We couldn't see any loss in the efficiency, torque, head, and power output in all the conditions, part load, BEP, and high load. In fact, we saw 2% increment in part load and less than 1% in BEP and no change in high load. So numerically, it is good, but we can see how the results are during the experiments. What is our current focus? We are trying to produce some drawings for the manufacturing of the Guidewing system and the draft tube cone. It is not yet complete, and it is still our current focus. Experiments will be performed in January, February 2021 at NTNU, Trondheim, Norway. And the Guidewings will be adjusted manually for the experiments at respective operating conditions. And once the experiments are done and successful, we will develop the code which can be modified and also applicable to any turbine model. That's it. Thank you for listening.
All right, thank you very much, Jesslyn, for your presentation. I would like to ask our audience if you have any questions or if you need more clarifications. Now is the time. You can also use the chat for posting your question. We have a couple of minutes for questions and clarification, so feel free to ask whatever you want.
Yes, Igor?
Yes?
Do you hear me? Philip here.
Yes, Philip, we can hear you.
Yes, hi. I have only one question about the boundary conditions of the reduced numerical model. Does the two-phase flow model is considered, or it's only one phase or just water? Yeah.
Just one phase model is considered because I guess it's cavitation-free experiment, so only the velocity profiles and the corresponding turbulent kinetic energy and the turbulent dissipation rate was considered.
Igor, can I ask a question? It's Jan Tore here.
Yes, Jan Tore, feel free to.
Yeah, I see the reduction in pressure pulsation amplitude. You said it was approximately 95%, which is tremendous. What do you compare with? Is it experimental data or?
No, this is with respect to numerical data of the reference Francis 99 turbine. We are waiting for the experiment to be done in January so that we will be sure how much reduction in RVR will be done with the reference experiment until results available.
Okay, but
Yeah.
if I'm not wrong, there are pressure pulsation measurements in this high head Francis 99 turbine.
Okay. I am not sure for the current reference model if there is any, like we are strictly sticking with the NTNU domain.
Okay.
Maybe I can comment here. Yes, we do have data coming from the Francis 99 workshops, but we have data for the reference design only, without any guideways or fins in the draft tube.
Yeah, but
Michel
that is
here.
the baseline.
Michel Cervantes here. I just want to add something. It's quite difficult to get the correct pressure amplitude, in fact, with numerical simulation. It's pretty sensible to time step, mesh, and stuff like that. So in fact, here we're investigating the concept numerically, and the baseline, it's the simulation without the guide vane, which give us a certain level for the pressure amplitudes. And after we're putting some guide vanes, and we're comparing the effect of the guide vanes with the base model without guide vanes. Comparing to the experimental data will be, we don't succeed really to match, in fact, the experimental data without guide vanes already. We don't know how to do it correctly. So here it's a relative difference between the base model and the guide vane setup.
Mm. Thanks for the clarification, Michel. Did that answer your question, Jan Tore?
Yeah, that's fine.
Okay, thank you.
Okay, Christer Abrahamsson here. What test head will be used in the laboratory?
Can you elaborate on that? I'm not sure if I understand it.
What test head will be used at the laboratory turbine model with the draft guide vanes installed?
Test
Yeah,
head.
which head, operating head, do you plan to use, Justin?
Yes.
I think we will use the Francis 99, so it would be 12 meter.
In the lab we have we can operate in an open and closed loop. So the open loop is easier to control, and that can produce 12-meter head.
Yes.
While the closed loop can go, I think we have done tests previously up to 30-meter head, which is of course according to the IC recommendations to have a sufficiently high Reynolds number, but that is for efficiency. So it's up to Jocelyn and LTU to decide which head they want to use.
Yes, as a manufacturer of turbines, I can see fatigue problems for the guide vanes in the draft tube at high head. Are you also considering these problems?
Yes, from the data available to us, we could only design from that perspective because not everything is available. So if I am right, I think it was the open loop because the maximum head was 12 meter in the Francis 1992 workshop. So from that perspective, the FSI result shows that it is quite within the safety factor of steel. So if we go above that, I'm not sure it will definitely break. But for considering whatever we have, this design should work. Rest is on experiments how it goes.
Okay.
Michel Cervantes here. We didn't do any fatigue studies. It's some static loading. Some we have been looking on the Guidewings. Of course, it may be some fatigue issue with time. At the moment, we are looking at investigating a concept, and so we don't have all the balls at the same time in the air at the moment. I have a question. Why for high-head machine you may get more fatigue issue in the draft tube than with middle or lower head machine?
Is this
it's a question for myself, so I understand and I learn. Because it was, I understood your question as with high-head Francis, it will be more fatigue issue in the draft tube. And so my question is why for high-head it will be more issue with fatigue in the draft tube than in middle head and low head?
Christer, will you answer, please?
According to conventional experience, the low head Francis turbines is most problematic at part load compared with the medium heads with a unit speed of about 50. These 50 RPM runners are the most smoothest ones, as I understand it.
Yeah, I suppose I have a comment here. Well, the draft tube fins have been successfully tested in the past. So to me, this is a little advanced, more advanced version of draft tube fins, ones that can change their angle of attack and open and close to align more with the flow. So of course there will be mechanical problems and strength problems that will have to be solved along the way. But I think for proof of concept and as a first step, of course, this is good enough, if you ask me.
Just a comment about the high head versus low head. I just think the condition in the draft tube when it comes to pressure and flow would be more or less the same.
Yes, that was my understanding too.
I have a question for Jaslyn. What will be the main focus of the experimental research, the experimental measurements? What are your plans?
The main focus will be on the pressure pulsations. So how much are they reducing, if they are reducing, and what is happening to the rotating and plunging mode. So far, this is what we have discussed for the first attempt, what we do. And then it is subject to further experiments. We also realize that we have two positions because there is a clearance for the upper Guidewing to move. So we will test at both the positions because which one will give the best result, I don't know. But so far, so good to answer your question. It will be focused on pressure pulsations analysis.
Yeah.
Yeah. Igor, can I add a small? Yeah, it as
Go
just
ahead, Michel.
Yeah, just a small comment to addition to. Of course, it is going to be pressure pulsation, and it's going to be efficiency for the machine. And it's since we have 3 guide vents, we need to have we're not using 2 pressure sensors. We need to use 3 pressure sensors. Because function of the position of your pressure sensor with a guide vent, in fact, you may be cheated in what you get.
Yes.
So you need to have a different setup of pressure sensors in your draft tube to analyze everything.
Exactly. Do you also plan to take a look at the cavitational performance as well? Maybe visually in the first step.
Visually, maybe an alternative. So, but I think we have a lot to do.
Yeah. Yes. Okay. Well, thank you very much.
I think it was a question from Anders Bart.
Yes, I have more question about the purpose and the philosophy and with the physics here. The Guidewings, they are handling a rather uniform inflow, and from that they create a smooth potential swirl here, and they have a number and chord length enough to make this work. Here we have a very uniform flow, and it's far from that jitter density which the Guidewings have. So as I understand the philosophy behind this, it is that the purpose is to make the vortex rope more disturbed, and because of that you reach the number 3 as optimum rather than 7 or 14, or so to speak. The vortex rope is disturbed by 3, divided in some parts of the vortex. It is divided in 3 smaller parts which are weaker and compensate each other and make the operation more smooth in low load area. Is that the right understanding of the philosophy behind this?
Jesslyn, you want to answer? Or
Jesslyn, thanks, Anders, for your question.
I can answer, then of course Michel can add over it. One point what he mentioned is correct, yes, but the other point is it's also redirecting the smooth flow coming in. So basically it is turning here midway the Guidewing, and because of that it is the vortex is converting into 3 smaller vortex. So yes, the redirection is the main idea from part load to BEP and at other operating conditions. And yes, Michel can add from here.
Yeah, just to if I understand correctly what you say, Anders, I agree with you. So ideally, we would like to have more guide vents in the draft tube to control the swirling flow, because in fact this swirling flow, it's the RVR which developed in the draft tube. It's due to the eye swirling rotating around this stagnant region, which creates an instability. So by putting guide vents, we are able to control this swirling flow. Other people want to control the axial flux of momentum, so we do the angular momentum. And ideally, we would like to have a lot of guide vents, but if we have too many guide vents, we are going to influence the efficiency. So we want to minimize the guide vents in order to optimize the efficiency, but we want to have the maximum number of guide vents in order to minimize the flux of angular momentum. So it's these three guidelines, it's the optimum that we find in some way at the moment.
Of course, you introduce a disturbance between the deflected flow and the unaffected flow, which could flow freely beside the guideways. But as I understand, that sacrifice, the losses introduced there are lower than the gain you have by deflecting the flow passing the three guideways.
Yeah, after so that it's a numerical investigation. So, but I think it's of interest to look after at the weighted efficiency of the machine, because it seems to be that for sure we get some wider operating range. We get a better pressure recovery and efficiency of the turbine at part load, and it seems to be that the effect at BP and high load it's minimal. So after it's about perhaps having a weighted efficiency and see what's coming out from what we gain at some part of the efficiency curve and what we lose on some part and so on.
Yeah, you lose. You said that the loss at best efficiency point was low. Is the wall functions really that accurate? So you are sure?
So here it's numerical simulation. So since we are doing numerical simulation, we're comparing some setup against setup, which are similar. So we're absolutely not right, but we are relatively similar. I don't expect the simulation to give a true reflection about what we're going to see in the draft tube in details, but it's a fingerprint of what we can expect and to go further.
Yep.
So it's relative. It's a design relative to a certain setup without guidance, and we move like that. Of course, the numerical simulation without the guidance have been validated about the experimental data of the Francis 99 workshop also.
Do you have any surface roughness on the guideways?
No.
Oh.
All right. Thanks for the clarification. We can conclude that this is a trade-off problem, and it's dependent heavily on the operational scenario for different turbines. I can hear Henning. Do you have a question?
Yes, please. I'm sorry, I was quite heavily booked, double booked in the morning, so I was not able to join in for the first part of it. So it's maybe you have discussed this before, but
we lost your audio, Henning.
Okay.
Can you go once again, please?
I can try.
Yeah,
Yes,
please.
Yes. I was double booked in the morning, so I'm not sure if this.
No, we are experiencing some technical difficulties here. Sorry, Henning, we cannot hear your voice clearly. It's kind of interrupted. Would you like to type your question or comment on the chat so that I can read it later?
Yes.
Thank you very much. We are also running out of time for this presentation. I see Philip has raised his hand, has a question, but we're gonna have to skip that part and move on to the next keynote speaker.